One thing we often want to do in trigonometry is work out the relationship between an angle and the length of a path on a circle defined by that angle. For instance, if we've got this circle here, we could look at an angle where the vertex of that angle is at the center of the circle, and we could see where that angle intersects the circle. Now, when we've done this, we have several things that we can measure about the circle. We can measure its radius. We can measure the angle itself, the size of this angle, and we can look at the length of the arc defined by it. So we've got these three different quantities we can look at. We will very often use the symbol S for the length of an arc on a circle defined in this way. And we want to know what is the relationship between S, R, and theta. We can get some general ideas by simply using our intuition about geometry. If R gets bigger, if the radius of the circle gets bigger and the angle stays the same, well then the distance S is going to get bigger. If we take a bigger circle, then a path that sits in the same position on that circle is going to grow bigger. Similarly, if we keep the radius the same and the angle gets bigger, we consider wider and wider angles, this S will get larger also. And we can have general things like this, but we want something more specific. And the excellent fact that we have is that when we're working with radians measures for the angles, the relationship between these three quantities is very simple. So when theta is measured in radians, then S, the length of the arc defined by the angle theta sitting inside a circle of radius r, is equal to simply r times theta. You simply multiply the radius of the circle and the angle defined by this, the measure of this angle in radians, and that will give you the distance along the circle. So, for example, if theta is equal to pi over 3 radians, which is also 60 degrees, but 60 doesn't work here. We can't use degrees here. If theta is pi over 3 and r is equal to 4, then the length of the arc defined by that angle inside this circle is pi over 3 times 4. We just multiply theta and r together and get 4 pi over 3. And that is the length of the arc defined by an angle of this measure sitting inside a circle of radius 4. We can do several things with this, and we've got other formulas that we can use that benefit from us using radians. So, for instance, let's consider also this same picture, but now, instead of considering the length of this arc, let's ask the question, what is the area of this sector? This angle encloses a particular sector, sort of a pie slice of the circle, and we can also ask, what's the area of this sector? Well, this one has a formula also. This one isn't quite as easy to memorize, so we'll also talk about how we can remember it, because it won't always be something that we recall immediately. Although the answer here is that A, the area of the sector, is equal to 1/2 r squared theta. Now, this r squared should remind you of the formula for the area of a circle. Remember that the area of a circle is pi times the radius squared of the circle, and that's actually what we're going to use to see why that is. So let's see why this is. The whole circle's area is pi r squared. Now, when we look at the yellow sector here, we're not looking at the whole circle, we're looking at a fraction of the circle. Well, what fraction of the circle are we looking at? We're looking at theta radians of the circle out of a total 2 pi radians of the circle. So theta, this is the angle, the total angle measure that defines the sector we're interested in, and 2 pi is the angle measure that you would take if you included the entire circle. So 2 pi radians goes all the way around the circle. We're not going all the way around the circle as we sweep out from one side of our angle to the other. We're only going theta radians. So we've got theta radians over 2 pi radians, and so we're looking at this fraction of the circle. So that means that the area of the sector is, well, it's the area of the whole circle times the fraction of the circle that we're looking at. And we're looking at theta over 2 pi of the circle. And notice once we do that we get some cancellation. The pi's cancel here. And from there, it's just a matter of rearranging things to get it into the form that we had before. So the 1/2 factor that we have here can come out in front and get 1/2 r squared theta. So we can, by using the radius, the angles, we can get relationships between those quantities and the lengths of the arc around the circle and the areas of the sectors defined by them, which wind up being quite useful for us in a lot of circumstances. All right, so let's look at an example where we can use this. Let's say we've got a circle set up the following way. Let's say that we are given that the radius of this circle is 6 meters. We've got a big circle, 6 meters, and then we're also told that this distance is 9 meters. And so we want to ask 2 questions. Let's ask, what is the angle measure of theta, where theta is the angle going between the 2 drawn radii of the circle? And we could ask, what is the area of the sector? That we've defined using these 2 radii of the circle. So let's look at how we would answer each of these. And we're going to answer the first question first, and that'll help us answer the second. So, for our solution, to find the angle measure of theta, we can use the equation S equals R theta. And as long as we're working radians, this is always true. So that for us, S, remember, is the distance around the circle. It's the length of the arc defined by the angle that we're looking at. So we have 9 is equal to, the radius of the circle has been given to us, that's 6, and then theta is what we don't know. So we get 9 equals 6 theta. But this we can solve for theta to figure out what theta is. So that means that we can divide both sides by 6 to get that 3/2 equals theta. So that means that this angle measure right here has a measure of 3/2 radians, 3/2 radians. So that's the answer to the first question. For the second question, we can use the formula that the area of the sector is equal to 1/2 r squared times theta. So for us, that will be 1/2 times 6 squared, because the radius is 6, times theta, which is 3/2. So working all of this out, we get 1/2 times 36 times 3/2, and we can do some cancellation. Remember, when you're multiplying fractions together, you can cancel things in the numerator and the denominator before you multiply, which usually makes things easier for us. So we can cancel the 2 and the 36, giving us an 18, and then we can cancel this 18 with the other 2, giving us a 9. And so when we multiply it all together, we just have a 1 in the denominator, which we won't write. And then in the numerator, 1 times 9 times 3 is 27. And the units for that are going to be square meters, because meters were the form of the lengths that we were given to begin with. So this is one of the ways that we can use these two formulas. If we have a figure involving circles and angles centered at the center of that circle, we can understand the exact quantities involved, both lengths and areas, very efficiently. Now there's another place where understanding the relationship between the arc length and the angle inside is very, very useful. And that's when we want to do problems involving angular velocity. So let's talk about that for a second. So the angular velocity of something defines, or describes rather, how fast something is rotating. So for example, a CD might spin at 3,600 revolutions per minute. So this is describing a speed, but it's not a linear speed. It's not telling how far something's going. It's telling how fast something is spinning. And in this case, the units involved are going to be a time unit in the denominator always, but then the numerator is going to be some sort of measure of angle distance, angle travel. So this is going to describe your angles. Now, it's very, very common in real life to encounter angular velocity described in terms of revolutions. How many times does something spin completely around in a minute or an hour or any other time unit? When we want to work with this, a lot of times we'll want to convert these units into either radians or degrees. So let's talk about how we convert between revolutions and radians or degrees. So our conversion factors are that 1 revolution is equal to 360 degrees, and that's equal to 2 pi radians. So using these factors, we can convert any angular velocity in terms of one of these types of angle measurements into the others. So, for example, the CD above spins at how many degrees per minute? Well, let's look at that. So for the solution, we'll look at 3,600 revolutions per minute. This is what we started with. This is the quantity we started with, and now we want to write down, we want to multiply it by a conversion factor that will change it into degrees per minute. So in particular, notice that the minutes are the same. We don't have to change the time part of the unit at all, but we want to change revolutions into degrees. So we want revolutions down here and degrees here. So we'll go back up to our conversion factors, and we'll see that 1 revolution is equal to 360 degrees. So when we multiply these two together, we'll get that 300 revolutions per minute is equal to 3,600 times 360 degrees per minute, which we can work out. So let's pull out calculator. So 3,600 times 360 is equal to 1,296,000. So that's 1,296,000 degrees per minute. And we can do the same thing, convert it into radians per minute or radians per second or per hour, or do any of the conversions that we would like that way. So let's look at how we can relate angular velocity to linear velocity, and the two of them are in fact closely related. So let's look at our picture again, and let's imagine that we have some object that's spinning around this circle going really fast. You could think of this as being some point on the exterior of a wheel, if this circle is a wheel, or even some particle inside a giant circular particle accelerator, something like this. And what we can do is we can measure a couple of different things about this particle. One of the things that we can measure is its angular speed. And that's based on how quickly it's traveling around the circle. So measuring how fast it travels around the circle measures its angular speed. On the other hand, if you were to take just sort of an instantaneous snapshot of what this object looks like at a point in time and look at what direction it's traveling, you can see it's traveling in the direction of the straight blue arrow. Another way to think about this is that if this object is being spun about on a rope, and then all of a sudden the rope is released, then that object is going to continue flying in the same direction. It's going to continue flying straight in the same direction that it was right at that instant when it was released. And so its speed that it experiences traveling forward is called its linear speed. And so there are two different ways that we can describe this object's speed. Its angular speed, how quickly it's going around the circle, and then its linear speed, which is sort of how fast it's going forward from its own perspective. Linear speed is what your speedometer would be measuring if you were on a car going around a circular track in this setup. So we want to relate angular speed and linear speed. Well, we can do this using our notion of how we calculate speed to begin with, and by using our formulas that we had before, assuming, again, we're measuring everything in radians. So recall that linear speed is equal to the distance traveled divided by the time taken. So if I want to calculate my linear speed, I ask, okay, how far did I go? And then I divide that by how long it took me to go there. If I travel 100 miles in 2 hours, I traveled at 50 miles per hour. And similarly, angular speed is equal to the angular distance. That is basically how far you went around your circle, divided by the time taken again. So what I can do is I can look at this object and I can fix a certain amount of time. I can say I'm going to look at this for 1 minute. And I'm going to measure two things. I'm going to measure how far it traveled along its path, so the literal length of its path. And then I'm also going to measure the total angle traveling that it did. How far around the circle did it go? How many radians or degrees or revolutions around the circle did it go? And in each of those cases, I divide by the time that it took, the 1 minute or the 10 minutes or whatever, and that'll give me my speed. Well, if we measure in radians, we have that S equals r theta. And let's remember what these are. The S is actually the distance traveled along this object's path. It's how far it actually travels along the arc of the circle. And theta would be the angular distance traveled. So we already have an equation that relates a couple of the quantities that we care about here. What we do now is we divide by time. We divide by the time taken to travel a certain distance. And so we divide both sides by t. So t here is going to be time taken. And now notice what we've got. Now, this s over t is exactly angular speed. Now we've got r over t and theta over t. We want to group up mentally the theta over t together. I apologize. S over t is not angular speed. I'm being quite silly there. S over t is the linear speed because S measures the linear distance that this object has traveled around the circle. Theta over t gives us the angular distance divided by time. So that does in fact give us the angular speed. And so we can get our formula relating angular speed and linear speed, and the point is it's basically the same formula. It's based almost exactly on the same formula that we had before. So we have that linear speed is equal to the radius times the angular speed. Now, often we will define the linear speed to be, or we'll use the notation v for the linear speed or the linear velocity. And the angular speed will often use the Greek symbol alpha for angular. And so what this means is that we have another equation which says that v equals r alpha, where v is the linear speed of an object, alpha is the angular speed of that object, and r is the radius of the circle that that object is traveling around. So we can use this relationship here to determine lots of interesting things about the problems that we want to look at. So let's see an example. A car's tire is rotating at 300 revolutions per minute, and it has a radius of 8 inches. How fast is the car traveling? So this problem is actually giving us information about angular speed. So rotating at 300 revolutions per minute, this is information about the angular speed of the tire. And then it's asking us a question about how fast the car is traveling. And this has to do with the linear speed of the tire. Because if we imagine the tire, it's rotating around, and then as it's rotating around, you could think of it as almost pulling the ground towards the car. And how fast is it doing it? It's doing that in terms of as fast as the tire itself is moving. So we could think of the points on the exterior of this car traveling around in a circle, and it's pulling the car along. Well, now we want to know how fast the car is traveling. So we want to know what the linear speed of this car is. So let's work sort of backwards on this one. We want to know the linear speed of the car. Now we can calculate that as the linear speed v is equal to r times alpha, the angular speed. Now r, we know this. We know that r is 8 inches. So now we need to find alpha, the angular speed. And in particular, we need to find the angular speed in radians. So the first thing we're going to need to do is to convert the angular speed information that the problem is giving us into an angular speed in terms of radians, not revolutions. So we need to convert 300 revolutions per minute into radians per minute. But we know how to do that. 300 revolutions per minute, we need to multiply by a conversion factor that has revolutions on the bottom and radians on the top. We know that 1 revolution is the same as 2 pi radians. And so that's the conversion factor that we want to use, 2 pi radians over 1 revolution. That's going to cancel the 2 revolutions, and so we're left with 600 pi radians per minute. All right, well now we're good, because now we know that the linear velocity is equal to the radians times the angular velocity. So that's going to give us 8 inches times 600 pi radians per minute. And that's going to leave us with 6 times 8 is 48, so that'll be 4,800 pi. Now let's think about these units for a second. First of all, it's definitely going to be minutes on the bottom. We're looking for a linear speed. We're looking for some sort of normal speed measurement, like miles per hour, or inches per minute. Inches per minute is a perfectly good speed, although we'll probably want to convert that in a second. So we can see that we get the inches here, but what about the radians? Well, remember that when we introduced radians, I mentioned that radians are technically unitless. Technically, radians are just counting how many times we're laying down radii of a circle around. And so we've included radians here because, in the last couple of lines, because we wanted to keep track of things and we wanted to have something on the top of of the fraction defining our unit. But now that we've got something else to put on top, we can drop the radians. So the radians are technically unitless. They're not a unit in the proper sense. They're just a count of how many times things are happening, which means we can drop. We can drop them when there's another unit that shows up in the process of solving the problem. Okay, so that gives us an answer, 4,800 pi inches per minute. There are a couple things about this that aren't super ideal. First of all, 4,800 pi is not a particularly easy to comprehend number. And in most practical applications, you'll want to throw this into a calculator in order to get an approximation for it, which won't be exact, but will be close enough for the applications or experiments that you're doing. However, possibly a bigger issue here is the fact that our units are now inches per minute. Now, the original problem, as I wrote it, didn't specify what units it wants. However, most of the time it will, and most of the time it'll define, the problem will define units for you to give your answer in that makes sense in the context of the problem. So instead of asking how fast the car is traveling without specifying, I want to add a little addendum here. I want to get our answer in miles per hour because that's a more natural way of thinking about how fast a car is traveling. That's something that that's easy to comprehend. And generally, you want to give your answers and solutions in ways that are easy to comprehend. So let's take a moment and take this answer, which is correct but not as useful, and turn it into a useful answer. So how do we make 4,800 pi inches per minute useful? So remember that there are two things we want to do. We want to convert to miles per hour, and we want to give an approximation to a reasonable number of decimal places. So which one do we do first? The answer is we want to do our conversions first. We want to do this first. And that's actually not because of anything special about conversions. It actually has to do with approximations. Approximations should always happen at the very end of the problem. So whenever you've got a problem where you're going to need to approximate, round to however many decimal places, etc., you always want to do that at the very, very, very end of the problem. And the reason for that is, whenever you approximate something, you are turning something exact into something that's not exact. It's a little bit off from where it was before, a little bit different. And when you do that at the end, that's not a problem because you'll know that I need 3 decimal places so that the number that I put down is really, really close to what I started with, or to whatever tolerance your application has. But if you approximate early in the problem, then that little tiny difference between the actual value and the approximate value can get multiplied. So any approximations you make at the beginning, any little tiny deviations from reality, will get magnified over time as you go through computations and further developments. So you always, always, always approximate at the very, very end of the problem and no earlier. So for this problem, we're going to convert to miles per hour first. So let's go ahead and do that. We've got 4,800 pi inches per minute. We need to convert to miles per hour. So we can do this in a couple of different ways. Let's handle the time first. We currently have minutes in our denominator. We want at the end, we want to have miles on top and hours on the bottom. We currently have minutes on the bottom, so we can convert from minutes into hours because we know that 60 minutes is equal to 1 hour. Now we can convert from inches to miles. Now you may know offhand how many inches are in a mile. I don't. So we'll have to do a couple of conversions here. So let's convert first from inches to feet, and I know there are 12 inches in 1 foot, and I know that there are 5,280 feet in 1 mile. So at this point, I think I'm done with my conversions, but let me just go and double check. So my minutes are going to cancel here. My inches are going to cancel there. My feet are going to cancel there, and scanning through what I've got only miles left on top. I've got only hours left on the bottom, so that means that everything has worked out. Now, if we were going to be keeping things exact, leaving things in terms of pi, we'd want to go ahead and reduce things here. Because we're going to be approximating everything at the end anyway, it doesn't make a huge amount of difference here. So let's just go ahead and multiply everything across on top, multiply everything across on the bottom. So without doing our approximations yet, because we want to do that at the end, we've got 4,800 pi times 60. Now 4,800 times 60 is equal to 288,000, 288,000. So we get 288,000 pi on top, and then on the bottom we get 12 times 5,280. We get 63360. And now, most of you have calculators, or you can access calculators like the one I'm using now through Desmos online that can do this whole division at once, including the approximation for pi. So we have something went wrong there. So we get 288,000 times pi divided by 63360. And I should have written down the units that I've got. I made a mistake here. 63360. And so we have that our answer is approximately 14.28 miles per hour. Problems that you complete online will have the number of decimal places they want specified if they want an approximation. So that answers the question back at the beginning. If our tires have an appropriate have a radius of 8 inches and they are rotating at 300 revolutions per minute, then that means that the car that they're attached to is traveling at 14.28 miles per hour. And so this is an example of how we can use the relationship between linear distance, angular distance, linear speed, angular speed in order to solve real life type problems.